Page 241, number 21. Let's see. Absorbency varies directly with the concentration of an unknown substance. So absorbency varies directly with concentration. So A equals K times C. K times C. I'm just using absorbency for Y and A for Y and C for X. The absorbency is, and that's why I used A and C, so it tells me the absorbency is 0.3. I know that has to go in for A for absorbency. When the concentration is 100. So now I solve for that constant there. I'm going to divide by 100, which gives me K equals 0.003. So the absorbency equals 0.003 times the concentration. Then it asks, find the absorbency when the concentration is 200. So the absorbency is 0.003 times 200, which is going to be 0.6. And then it asks the second question, find the concentration if the absorbency were 0.15. So you put the 0.15 in for A, the absorbency, and you're solving for C. So you would divide by the 0.003. And that concentration is 50. So I was asking two separate questions kind of at the end. Okay, perfect. You bet. That was your only question? Cool. Corrections on the last test, make sure you get those corrections done and to me. Please have those to me by next week so I can get them graded. On this test here, I will grade them and I'll get them back to you. And to Richmond, I'll just email it directly to your WITC account. So I'll email those back to you as soon as I am able to. Probably won't be until sometime Monday afternoon because they usually don't get emailed to me until later in the day Friday. So they'll probably won't get here until I'm gone for the day Friday. But Monday, that'll be my first priority is to grade those and email them back to you. You will have, and then in Rice Lake here, hopefully by about 2:30 in the afternoon Monday, if you just stop by the classroom here at any point, I should have them for you. Or if you want to wait around the Friday morning, maybe I can get them graded too and have them for you. But you have corrections due. Let's just do this. Corrections on test 3. Those are going to be due by May 11th. That'll be next Friday. Then corrections on test 4. Those are going to be due by May 17th. That'll be a Thursday. That's the last day of class. And then homework. And this homework technically comes from chapters, I think there's 1 page or 2 pages in chapter 6, 9, and 10. That will be due by that Wednesday, May 15th, so that you can keep it for using on the test if you want to. For that test 4, again, you will be able to use your notes in your books. I realize we've crammed a lot of material into this one. So you will be able to hold on to your homework. Those of you that have sent me homework, you'll notice I've graded it and thrown it in the grade book already in Blackboard. Otherwise, none of it's official. None of it will be late until after May 15th. Does somebody have a question there? I saw a hand up. Yeah, if you've sent some of it in, I've already graded it and put those points in Blackboard so that I know it's been turned in. Okay. Perfect. Okay, let's go ahead and get rolling then. Today we are talking about statistics. And we actually did hit on a little bit of this last week when we talked about those organizing data. When we did the data tables and the graphs, the frequency table. And then, of course, the graphs. And there's a wide variety of graphs that most of us have seen before. Bar graphs, pie graphs, or circle graphs. The biggest thing with the pie graphs and circle graphs is typically you're dealing with percents. There were line graphs and other sorts of graphs that we've all seen. So I'm not going to spend any more time looking at organizing data. I could go on for a long time discussing why we organize data and what are some of the advantages and the pitfalls and stuff of doing it, but we don't have that kind of time. I do want to talk a little bit about some of our vocabulary for statistics. Because statistics itself is kind of another language. Some of the words mean what we would think they mean, and other words are kind of different from what we normally would use them for. The most important thing in statistics is something called a population. And a population is a group. That could be people, it could be items, it could be a medication, it could be parts coming off an assembly line. Any group of things that we desire to learn about. Now, this might not be as easy to define as it seems. A lot of people look at this, oh, that's pretty simple. But we went through a presidential election about a year and a half ago. Let's look at an election. We want to predict who will win the next local election. Well, it's really easy to look at that and think, well, what we want to learn about is the candidates. Which candidate's going to win? But that's not really who we're trying to learn about. The candidates themselves, while they influence the election, really are not the ones that determine the result. What we really want to learn about here are population. Really comes down to voters. Now, again, we have to be very precise. You could say, well, all registered voters. Well, the problem there is the registered voter that stays home that day really doesn't have anything to do with who wins the election, do they? So really our population is voters who will vote in that election. The information we would draw from a population would be called a parameter. So I'm going to have to replace my battery here. And a parameter is a result, the result from, hopefully I can spell today, from a whole population. Now, a lot of people say a parameter is something that describes a whole population. You have to be very careful with that because, okay, all voters who will vote in the next election, you say, well, they're all over 18 or all 18 and over. Well, yeah, that does describe the population, but that isn't a parameter. The parameter has to do with what it is we're trying to learn about them. So a parameter might say that 57% will vote for candidate A. That would be a parameter because that's what we're trying to learn about. Well, we almost never study a full population. If we were to try to gather information from a full population, it's called a census. Our government does a census about every 10 years. In fact, they're gearing up to start another one here in 2020, where they attempt a census. They've never succeeded, really. There's always at least some people who do not respond, but they try to gather information from every person in the United States. Not very practical to do that in most cases. In honesty, I've been waiting to see our government drop the census. The main reason we still do it is that's the way we base our congressional districts. It's for every so many members of the population, we have a congressional district. So that's how they redistrict them. There needs to be a more efficient way to do it. There is literally billions of dollars spent on doing a census. It's very expensive to try to do. So most of the time, rather than studying a population, we study a sample. And a sample is just a smaller group from the population. Why do we use a sample? We already hinted at some of them, some of the reasons. Expense is one. It's very expensive to try to gather information from a whole population. It's cheaper to go to a smaller group or a sample. Time is another. It takes a lot of time. Well, time and money are always kind of tied together, right? Your time is worth something too, so the more time it takes, the more it costs. Difficulty defining a population is one of them. Up above, we saw in that local election, some people don't know if they're going to vote in the election yet, so we're not sure if they're in the population we want to study or not. So that's another reason we'd take a sample rather than trying to gather from everybody in that population. This next one, it's hard to word it right, so I'll just try to explain it here. Time sensitive. What that means, okay, let's say I am going to try to survey everybody in the city for a mayoral election. It's going to take me like 4 or 5 days. So let's say I spend 2 days calling people, asking them which candidate they plan to vote for. Now, they can't really tell me if it's 2 months before the election. They can't really tell me for sure who they're going to vote for in 2 months. What I'm really asking them is, if the election were today, who would you vote for? So let's say I spend 2 days doing that and I'm about halfway through the city, and then one of the candidates gets arrested. Well, the next day I start calling people. Am I working under the same conditions? No, I'm not. So many of the people I've already talked to would have changed their answer if I had called them that day on the third day. So you would have to start over. You have to, it's what they call a snapshot. Ideally, a survey would be done in an instant. You would pick a time at 3 o'clock in the afternoon on Monday, and you would like survey everybody all at once at 3 o'clock in the afternoon. Everybody would be surveyed all at once. That would be the most accurate data. I mean, even starting to call them at 3 o'clock and calling until 7, something might happen in that small window of time that changes people's minds. So it's very tough to do a survey and keep it that way. There are all sorts of other reasons. The last one I'm going to put in here is destructive testing. This is obviously not part of a survey. What this would be is an industrial quality control. Let's, for example, so we're producing parts and that part has to meet a certain standard, it has to be so strong. We might take a part off the line, put it in a machine that stretches it until it breaks to see how much force it held. Well, if we test every part, they're all broken, so there's nothing to sell. So you would take a sample and test enough of them that you're comfortable that the rest of them are strong enough if that sample is strong enough. And then, of course, the final reason that is just a huge debate in statistics, this was the one I could probably go on for 3 or 4 weeks worth of class about, is ethics. In the medical fields, that's the one that's always the defining characteristic. We could test this drug, but where's the ethical line? Where is it? What do we have to do to establish that it is worthwhile to test it on humans or whatever next step? The biggest thing about a sample, of course, a statistic is just like a parameter, but it describes a sample. So we might take a sample of voters, call them up, and we might have 59% of our sample said they were going to vote for candidate A. That's a statistic that describes our sample. After the election, we might find that 57% of the people voted for candidate A. That would be a parameter that describes the whole population that voted. So when we're looking at a sample, what we're looking for is something called a representative sample. Representative sample means that the sample statistics are approximately equal to the population parameters. There are a few ways to do that. One thing that we have to worry about is sample size. I could not just walk out this door and ask the next two people I see, hey, who are you going to vote for in the next election? And one says candidate A, one says candidate B, and I just, hey, it's a 50-50 split. It's a dead heat. That is not a big enough sample. We're not going to say much more about that because there's a lot of arguments depending on which textbook. Statistics has a couple of different schools of thought, and depending on which one you're working with at the time, there's different standards that are set for sample size. So we're not going to get into that debate. Yeah. Mm. It wouldn't be in most cases. I mean, looking at a survey, you're not going to destroy anything. But there is, there is things you can do that influence, change the population by surveying them. The more you ask somebody a question, the more they get annoyed. Yeah. But I mean, destructive testing does only apply to a small group of possible tests. So that random selection, I didn't say anything about that. Random selection means that everybody in the population has an equal chance of being chosen. The best example I have there is, let's say you go outside a rally for one of the candidates and you interview people, you ask them on their way out, you survey them on their way out who they're going to vote for. Well, if they're at a rally for that candidate, there's a good chance they're going to vote for that candidate. So you're not getting a very representative sample there. You're not getting a good random selection. Unbiased process. This is where that ethics comes in. And again, like I said, you could go on for a long time talking about ethics. There are companies that pay big money to bias the process of statistics. And what I mean by that, let's say that your local school district needed more money to improve, to update some things in the classroom, which meant they were going to have to do a tax levy change, which means it has to go to a referendum. So if you get a survey question, your survey question starts out, would you be willing to pay a little bit more in taxes every year to support better education for our kids? What's the first thing you heard come out of my mouth? More taxes. You've heard more taxes. A lot of people do not even hear the rest of that statement. Heck no, I'm not willing to pay more taxes for the year. I don't care what it's for. Don't want to pay any more taxes. But if you word it the other way, if it meant improving education for our kids, would you be willing to pay a few dollars more in taxes? Well, you heard improving education for our kids. There are many people, yeah, I'm for it, whatever I have to do. They don't even necessarily hear the rest of the question. There's a lot of work that has been done. That's why when you get some of these surveys, they might be 20 questions, but it's 10 questions that are asked twice in different ways. the different wording. They actually do that on purpose to see if you respond differently to different wording of those questions. It's the same question, but whatever topic is mentioned first might influence how you answer it. The final thing I wanted to put in here, something called outliers. Even in populations, there's data that doesn't fit. And then how do we handle that? Now that's going to be beyond the scope of this course. We'll talk about it a little bit when some things come up, but we can't get too detailed on how do you determine what doesn't fit and what needs to be. Sometimes if it doesn't fit, you take it out of your statistics, out of your calculations. In the medical fields, this happens a lot. In medical studies, if you look at a drug test or a clinical trial for any medical process, the last several pages are going to be what's called exceptions. And you look through there and you might see, okay, they're doing an experimental procedure on someone. And during that procedure, they find out that person has, like, I don't know, a level 4 colon cancer. They're probably going to die within 6 months anyway. That person's going to be taken out of that study because the procedure that they're performing isn't going to affect the outcome of their life. Or you have someone who's in a drug test and they die in a car accident. Well, their death is not part of that drug test. That would have happened whether they were on the medication or not. So that person is excluded then from the results of the study. So things that need to be excluded, data that needs to be taken out because it's affected by either outside factors or something so extremely unusual happened that you shouldn't ever consider it because the chances of it happening again are very unlikely. They were going to die without taking the drug or not. So let's start looking. We looked last week at summarizing data, organizing data graphically and with tables. Today we want to look at summarizing data numerically. And we see these statistics a lot, and we think we know what they mean. There's actually a bigger picture behind it. What it all comes down to is something called a data distribution. Now, there are two different types of data that we discussed last week. We talked about that categorical and that numerical. So today we're looking mostly at numerical data, where we're asking a question and the response to that question is going to be a number. So let's say we want to look at scores on this last test, test 4 historically. Now I'm making stuff up here because normally I split it up and I do 2 tests, 4 and 5, instead of putting it all together in one. So I'm just going to be making some numbers up here just so you're not nervous about what I put up here. Our data distribution can start out as a number line using something called a dot plot. And so the number line that we use has to go from the at least the smallest value possible up to the largest. So let's say that the smallest score we've ever had on this test was an 80. And of course, the highest score would be 100. So what we'd do is we would actually take those tests and when we grade them and score them, we'd plot them on here. Let's say the first test scores 91. The second test scores 87. So put a dot above the 87. The next one's a 95, then a 96, then a 92, and another 91. And as I score these tests, I keep putting dots on the number line. You'll notice when a number is repeated, I just put the dot above the other dots above that number. And what starts to form here is a shape. And this shape is called a data distribution. And you can see it kind of takes on a predictable shape here. If I draw a line through the top dot in each column, it makes a shape like that. Now, many of you might be familiar with this shape called a bell curve. The official statistical name for it is called the normal curve or normal distribution. It's called the normal distribution because in nature, that is the shape that most data normally takes on. The distribution of heights of people of the same age will take on a normal distribution. Distribution of of weights will take on a normal distribution by age. Distribution of scores on a well-written test should take on a normal distribution. I don't know if any of you remember the high school state testing that you did. They called them a norm reference test. That's because those scores took on a bell curve, a normal distribution. So as I'm looking at that curve, if I wanted to describe that curve to someone, there are a couple of things that could be used. Like, for example, this blue curve here, one of the first things I would use to describe it is I would say its center is about at 90. Now I might have another curve how would I describe the difference between the blue and the green curve? Well, I'd say the blue curve has a center at 90. The green curve has a center at about 92. They have different centers. So that is one thing that can be used to describe these bell curves is their center. We're going to look at different ways of describing their center numerically. Well, the other thing we could have, the other difference we could have would look like this. Now this red curve has a center that's still at 90. How would I describe the difference between the red curve and the blue curve? Steeper, narrower. The blue curve is more spread out. That is called spread or sometimes called dispersion. Those two words mean the same thing. So those are, and then there's a third one that's sometimes considered that looks more at just basic single numbers as location within that distribution. We'll talk about that a little bit. That'll be one of those topics that if we get time, we'll get to at the end of the class. So let's talk about those measures of center first. So to make this work, I've got to have a set of numbers. So I'm going to put a set of numbers down here a little ways so that I don't scroll past them. Two, three, four, five, six, seven. We'll put one more number at the beginning here. So I got 9 numbers. Let's do 17. So I got 17, 5, 13, 9, 22, 15, 11, 10, and 13 is my set of numbers. If you're wondering where those come from, yeah, we just made them up. So our measure of center, our first measure of center, I'm going to start off with this one because it's the one that most of you are probably familiar with. The mean. The mean is what most of us usually refer to as the average. Now some mathematical symbols here for you. The letter little n is the number of items in a sample. So for this sample I just made down here, what's n equal? 1, 2, 3, 4, 5. Yep, 9 of them. N equals 9. So n is the number of items in that sample. Little n would be sample, big N would actually be the number of items in a population. This symbol right here that looks like kind of a funny, bless you, looks like kind of a funny E. is sum. Add them all up. And X stands for each number. So the technical definition of mean is the sum of the x's divided by n. What does that really mean? That means add them up and divide by how many are there. So I would do 17 plus 5 is 22, plus 13 is 35, plus 9 is 44, plus 22 is 66, plus 15 is 81, plus 11 is 92. I'm running out of space. Plus 10 is 102, and plus 13 is 115 divided by 9, because there's 9 there. So it's 115 divided by 9, which gives us, what does that come out to be? 20 or 12.78 about is our mean. We divide that out. Is that right? So 12.8, 12.78. On a test, I would tell you what to round to. In the homework, you have to make sure you see what they tell you to round to as well. So that is the mean. You just add them up and divide. This, like I said, it's what we've always discussed as the average. The next one is called the median. The median is the middle number. So the median actually involves some steps. Step one, we have to put the numbers in order. So I have to go to my list over here and I have to put them in order from smallest to largest. Let's say I've got what, 5, 9, 10, 11. What's next? 13, 13. 15, 17, 22. Is that all 9? Yes, it is. I'm going to leave them numbered 1 through 9 anyway because we're going to need that in just a second. Step 2 is to find the location of the middle number. Now, this process can be done one of 2 ways. The first way, if n is odd, which in this case, n equals what? 9. So is n odd? Yes, it is. So when n is odd, do n divided by 2 and then round up. So what does that mean? 9 divided by 2 equals what? 4.5, which rounds up to 5. So the 5th number in our list is our median. So the median here is 13. Notice that was really close to our mean. Our mean was 12.78. So I just took n, which was 9, divided by 2 to get 4.5, rounded up to the next whole number of 5, telling us the 5th number in the list, when they're put in order, is the median. If n is even, I'm going to have to make up a new set for us here. I'm going to just put this set in order as I make them up for you. In this set, what does n equal? 6. Very good. So since n is 6, n is even. So we're going to do n over 2, and it is between that number and the next. Let me show you what I mean there. N is 6, so 6 divided by 2 equals 3. So that's telling us it's between the third and fourth number. The third one is 12, the fourth one is 13. Mathematically, how do we determine between? We add them together and divide by 2. When you do this, by the way, make sure you hit equals before you divide by 2. Remember, order of operations, division would happen before addition. So you have to hit 12 plus 13 equals 25. Then divide by 2 to get 12.5. Because if you just did 12 plus 13 divided by 2, the calculator only divides 13 by 2 and then adds it to 12. You get 18.5, which is way off. So that would be 12.5 is the median of that set of numbers. Any questions so far on mean or median? Next, we have the mode. The mode is the number that occurs the most often. So back up to our original data set, not this new one here, but back up to the top. Usually it's easier when I use the ones I put in order for the median. What number here occurs the most often? 13 is the only one that appears twice. So 13 is my mode. Now in a large data set, the mode is very useful. In small data sets like these, the mode usually isn't terribly useful. And a lot of times there aren't any numbers that are repeated more than once, or there's 2 numbers that are repeated twice. This is where that different schools of thought come in. Some textbooks would say you can have 2 modes, you can be bimodal. Other textbooks would say if you have a large data set, you can have multiple modes. For this class, there's either one mode or there is no mode. So if there isn't one single number that appears most often, there is no mode. The mode is really the most useful for categorical data. Why do I say that? Well, on categorical data, you cannot calculate a mean because there's no numbers. What is the mean of the colors red, blue, and green? Well, we can't do anything with that. There's no median there either. But we can say which one was selected the most often. That would be the mode. Then there's also something called the mid-range. The mid-range is kind of a quick and dirty calculation. It involves something called the max and the min. The minimum is just the smallest number in the list. The maximum is the largest number in the list. The mid-range is found by averaging those two together. So again, we look back up at our list. The smallest number was 5 and the largest number was 22. So the minimum is 5, the maximum is 22. We add those together. 5 plus 22 is 27. Divided by 2 is 13.5. That's a little ways off from the others, but not too bad. That is the mid-range, yes. Yep. Again, the main usefulness of that is just as quick and dirty. You just have to take 2 numbers and combine them. Now, in a perfect normal distribution, these 3 numbers, we're going to ignore the mid-range for now. Pretend that's symmetrical. Let me try that again. That's a little bit closer to symmetrical at least. In a perfect normal distribution, it should be perfectly symmetrical. Of course, the mode is the highest part of the curve, right? That's the number that occurs the most often. The mean should be that same number. And the median should also be that same number. In a perfect normal distribution, the mean, median, and mode will all be the same number. But we all know that distributions aren't perfect. So we talk about skewed. A distribution is skewed to the left. The curve is stretched out to the left like this. The mode, and I'm just going to put the mode in blue here because that's what I did for the first one. For color code, the mode is still that highest point. The median is going to be in purple. The median moves over a little bit in the direction of the skew. The mean moves over a lot. Depending on how skewed it is, the mean moves the furthest. It always moves the furthest. So if you calculate the mean, median, and mode, by comparing them, you can tell which way the data is skewed. So if it is skewed right, the opposite happens. You can see this curve is stretched out to the right. The mode is still the highest point of the curve. The median gets moved over a little bit. The mean can get moved over a lot. So the question becomes, which is the best measure of center? Well, I've already told you that the mode is really best used for categorical data, not terribly helpful for numerical data. So this question really is coming down to the mean or the median. What do you guys think? How many of you, show of hands, would say the mean? How about the median? How about don't care? What do you think is the best measure of the center of a set of data? The mode? The mode really is only good for categorical. Between mean and median, a lot of people would say the mean because you got that formula and you crank out numbers through it, right? It feels satisfactory. If you look up here, you said the mode, and I didn't mean to like shoot you down categorically like that, but mean or median? Sure. There is something with the mode. It's called stability. You can see the mean is the one that moves the most. It's the most unstable, or what's called not resistant to outliers. Let me show you what I mean by that. I can't remember the year. I don't remember if it was 1983 or 1984. So I'm just going to say 1983. With that quality, it might have been 1984. Well, you want the one that's the most descriptive but still stable. So that would be usually the median, but let me show you why. University of Virginia. Their BS in marketing degree. They published that the average starting salary that year was just over $78,000 per year. Now, to put this in perspective, back in 1983, 1984, the average high school teacher was starting at $16,000 or $17,000 a year. So $78,000 a year was an incredible amount of money. $78,000 a year, I might be tempted to be gone tomorrow. Just saying. It's still a pretty good paycheck. What they failed to disclose was that one of the graduates who actually did graduate with a degree was a man by the name of Ralph Sampson. Ralph Sampson was 7'4" tall. He was both his junior and senior year of college. He was the NCAA Basketball Player of the Year. He was the #1 draft choice in the NBA draft. Went to the Houston Rockets. You can guess how much money he got paid. In the early 1980s, basketball, NBA was the highest paid sport in the world, in the United States. Multi-million-dollar contract. Now, can you imagine how many $20,000 a year marketing graduates it takes to average out a multi-million-dollar contract to $78,000 per year? Mr. Sampson was the only one in that group that made more than $33,000 that year. Obviously, the $78,000 was a mean. The median was about $23,000. Yeah, that's the median. Well, it's the median. I mean, this is the actual mean. Is that an accurate statistic? Yes, it is. Is it ethical to publicize it? Probably not. It's very misleading. Because only one person made more than that. Everybody else was below 33,000. Okay, so our next step then. Let's talk about measures of spread. So for this, I'm going to give us another set of data. A little bit smaller because this calculation can be a little more complex. So let's do 7, 13, 11, do 15 and 24. There's our set of data. For spread, the first one that we're going to have is the range. The range is simply kind of like the mid-range, max minus min. The biggest minus the smallest. So what's the biggest number in that list? 24 is the max. What's the smallest number in the list? 7. So 24 minus 7 is 17. So if we want to look at how good something is for a measure of spread, we look at something called the ability to discriminate. So I have that list of numbers there. I'm going to write another list of numbers here. It's going to have the same range. The range is still 24 minus 7. It's still 17. Would you say that set of data is the same amount of spread? Let's take a look. We're going from 7 up to 24. So that first set of data, we have values of 7, 13, 11, 15, and 24. That second set of data, we have 7, 8, 13, 18, and 24. I would say the purple dots are spread out more than the brown dots are. They're definitely not distributed the same. So the range is not a very good measure of spread as far as discriminating between similar sets of data. So we have something called the standard deviation and the variance. I read them together because the process for calculating them is really the same process. There's just one more step to find the standard deviations. These are very closely related. So I'm not going to give you the formula for this because the formula is listed in the book. The formula itself is difficult to understand. What it really is a 6-step process. So what we're going to do is we're going to give you the 6 steps. So we're going to start out by using this top data set. And we'll do the 6 steps. Step 1 is to find the mean. So the mean of those numbers, again, we're going to add them up. 7 plus 13 is 20, plus 11 is 31, plus 15 is 46, plus 24 is 70, divided by 5. 70 over 5 is 14. So 14 is our mean. I don't want to get ahead of people, so I'll give you a second to catch up. Step 2 first set up here. So step 2 is to subtract the mean from each number. What does that mean? Well, I'm going to take my numbers here, 7, 13, 11, 15, and 24. And I'm going to subtract that 14, that mean of 14 from each of them. So 17 minus 14 is negative 7. Sorry, 7 minus 14 is negative 7. 13 minus 14 is negative 1. 11 minus 14 is negative 3. 15 minus 14, 1. And finally, 24 minus 14 is 10. Now, the numbers I just calculated here are referred to often as the deviations. Sometimes referred to as the deviations from the mean. That's how far each number is away from the mean. Step 3 is to square each deviation. So we have negative 7 squared. Now be careful on your calculator. Notice I put those parentheses in there. You have to do that on most of your calculators as well. If you don't, it'll give you a negative number. Any number squared is always positive. Yeah, the little minus down by the equal sign and the ones in parentheses. X squared should be on there. Yeah. So negative 7 squared is 49. You can just do negative 7 times negative 7, 2 words. So like on this one, I would do parentheses. You got to do this negative now here, not this minus sign. Negative 7, close parentheses, and squared. So now negative 1 squared is just positive 1. Negative 3 squared is 9. 1 squared is 1. And 10 squared is 100. This list is often referred to as the squared deviations. Makes sense, right? I realize we're up on break time. We'll finish this example, then we'll take our break. Step 4 is to find the sum. So 49 plus 1 is 50, plus 9 is 59, plus 1 is 60, plus 100 is 160. That is referred to as the sum of the squared deviations. Step 5 is the tricky part. Step 5 is divide by n minus 1. What is n again? How many items are in the list, right? So for this list, what's n? 5. Very good. N equals 5. So that means that n minus 1 is 5 minus 1, or 4. So for this set of numbers, we divide by 4. 160 divided by 4 is 40. That number there at the end of step 5 is the variance. If you're asked to find the variance, that's the number they're looking for. If you're asked to find the standard deviation, there's one more step. And that step is step 6. It's the square root. So square root is that symbol. So the square root of 40 is 6.325. That would be the standard deviation. Okay, at 9:23, let's take our break quick. We'll come back at 9:33 and we'll pick up with those measures of spread. Let's see how you're doing on this. So the first step is to find the mean. You'll notice we get the same mean of 14 as we did on the last one. Second step is to subtract the mean from each. So 7 minus 14 was negative 7. 8 minus 14 was negative 6. 13 minus 14 is negative 1. 18 minus 14 is 4. And 24 minus 14 is 10. So that is our deviations. Next, we had to square them. So negative 7 squared is 49. Negative 6 squared is 36. Negative 1 squared is 1. 4 squared is 16. And 10 squared is 100. How many of you made it that far, at least? Okay. Are you using the old set? Step 4 is to do what? Find the sum, add them together, and we get, what, 100 and 202? Step 5 is where it got tricky. What do we do on step 5? We're going to divide by n minus 1. Since n is 5, we divide by 4, which means we get 50.5. That number there, by the way, would be the variance. But we weren't asked for the variance. We were asked for the standard deviation. How do we do that? Square root. Square root of 50.5 is 7.11. Now you notice that's bigger than the 6.325 we had up above. So that does tell us that those numbers are more spread out. So that standard deviation is able to discriminate between those two data sets, where the range was not. So now the big question comes up, why do we care? How does this center and spread help us with anything? Well, let's go back to this normal curve. Now what I'm about to put up here is in your book on page 355. Your book uses numbers a little bit different than what I'm used to. But I'm going to use the numbers that are in your book. So your bell curve, looking something like that, is divided up in a very specific way. The center of that bell curve, if it's a perfect distribution, should be the mean, the median, and the mode, right? So we can use either any of them. We're going to use the mean as the center of that. Then we go out in steps of a standard deviation. So this is -1. SD is standard deviation. -2 standard deviations. -3 standard deviations. Now we're going to come back and put some numbers in there in just a minute. We can go the other direction as well, going above the mean. +1 standard deviation. Next step would be +2 standard deviations, and then +3 standard deviations. Something called the empirical rule, which just goes off these normal probabilities, states that between 1 standard deviation below and 1 standard deviation above, about 68.3% of the data will fall in that range. From 2 standard deviations below to 2 standard deviations above, 95.5% of the data will fall in that range. From 3 standard deviations below to 3 standard deviations above, 99.7% falls in that range. So at this point, I'm guessing you got a little confused. What ranges? What do we mean by -3 to +3 standard deviations? Well, let's say that for this, now these percents never change, by the way. So let's say for this data set, we have a mean of 40 and a standard deviation of 8. What that means is the mean here, this center number is 40. The standard deviation of 8. So -1 standard deviation would be that mean minus 8, or 32. Minus this 2 standard deviations would be subtracting another 8, which would make it 24. -3 would be subtracting another standard deviation, or -8 would be 16. Going the other way, plus a standard deviation would be 40 plus 8, or 48. Plus 2 standard deviations, 56, and plus another one, 64. So what that's saying, for this set of data, we would expect 68% of the numbers to be between 32 and 48. We would expect 95.5% to be between 24 and 56. And we would expect 99.7% to be between 16 and 64. Now, I think this distribution is a little bit more powerful if we break it down. So I'm going to do this. 68.3 divided by 2 is 34.15%. That's 34.15% in each of those. So if 68.3% is between 32 and 48, between 32 and 40 is just half of that, 34.15% of the data. As we go out here, 95.5 minus 68.3 gives us 27.2 that's split between here and here. We divide that by 2, that is 13.6%. Here and 13.6% here. If I were to add these percents up, all 4 of those percents, I would get the 95.5. As I keep going out, this, of course, is 2.1% then here. I just found the difference between what I already had here, and then what that next number was, and then whatever that difference was, I split it between the two ends. So 2.1% here and 2.1% here. And then, of course, that means there's 0.15% outside of the 3 standard deviations on both ends. Now, in this setup, when we have a normally distributed set of data, these numbers up here, these percents don't change. If I want to use those, or I could use these percents don't change. Those are just 2 different ways of writing the same percents. These numbers down here change for every set of data based on the mean and standard deviation. Does that make sense? So let's take a look. If you want to redraw that curve with the percents, redraw everything above this line. I'm going to give us some new numbers and we're going to do it. All the percentages never change. That is every normally distributed set of data has those same percents. What I'm going to do is I'm going to change our mean and standard deviation. So like I said, those percents, that part of the curve will never change. The percents will never change. What changes is the numbers that go down here because of the mean and standard deviation of our data set. Let's say that you are looking to buy a house. And you want to buy three bedroom, 2-bathroom house. And you've done your research in the area that you want to move to. What you found is in that area that you're moving to, over the last few years, you've taken the price of all homes that have sold that are 3 bedrooms and 2 bathrooms, and you found the mean selling price is $119,000 with a standard deviation of $24,000. So what that means is the center of this curve would be 119,000. I'm just going to write 119. What number would go here? 119 minus 24 would be 95. How about here? 71. Right? 95 minus 24 would be 71. And finally here, 47. So notice the percents didn't change. It's just the numbers down here that are changing based on our mean and standard deviation. So up here, +1 standard deviation would be 143. That's just 119 plus 24. +2 standard deviations, 167. And +3, 191. Now let's say you find a house that you just absolutely love, but the listed price is $167,000. But it is 3 bedroom, 2 bath. Your agent is telling you you better put in an offer now. This house isn't going to stick around very long. Well, how do you analyze that? Well, we look at this here, 167,000 is right here. That means right there. If we look at the numbers that are larger than 167,000, that's 2.1 and 0.15. That's 2.25%. What that's saying is only 2.25% of houses with 3 bedrooms and 2 baths sell for more than that 167,000, which is telling you one of 2 things. Either you're probably going to be able to get that person to take, that homeowner to take less for their house, or if they won't, you're probably going to be able to find a house that you still like, that you can buy for less. Because the other side of that, if I added up the percents going this way, those would add up to 97.75% that are cheaper, that sell for less. I'm pretty sure in one of those 97.75% you can find one you like. So this is a way of comparing numbers within themselves, basically. Actually, I did. What I did is I compared. I also run a construction company, so I compared it to cost of materials. The house I bought was in foreclosures, so I bought my house literally for less than what I could buy the materials to build it. So that's the joy of the economy going down, right? Pretty much. Let's look at, you want to do starting wage. Actually, you've been offered a job, and your job offer is offering you a starting wage of $24 per hour. You do your research, and in that area, you find that for starting wages of all jobs in that area that are in the same class as what you're looking at, the mean is $21.50, and the standard deviation is $2.50. So what that means is we start our bell curve. What number goes at the center of this bell curve? 2150. If we go up a step, what number goes there? Plus 250 is 24. What's the next step? Plus 250 is 2650. And the next step? Plus 250 is 29. Now notice I'm only filling in that right side because the number we're looking for is the 24. That's right here, isn't it? I don't need the rest of those numbers. But I can pull down these percents. I've got the 3415, 13.6, 2.1, and 0.15. So I want to evaluate, do I think $24 an hour is a good starting pay? Well, let's say I want to know who gets paid more than me or how many get paid more than me. I would add up those percents of all the numbers to the right, larger. That would be 13.6 plus 2.1% plus 0.15%. That's 15.85% of people get paid more than that, starting, which means you're getting paid more than 84.15% of people getting started. That makes, so that's probably a pretty good starting pay. So that is one way, using that bell curve like that and those percents. And like I said, those percents never change. Those will always be there. Is one way to compare numbers to other numbers in the same group. What if I want to compare to a different group? Well, to compare to a different group, we use something called a z-score. And a z-score works on a similar concept of what we did up above. I'm finding those percents, that empirical rule that we just did. But what it does is allows us to compare one bell curve to the next. This is sometimes called normalizing. If you ever hear that term in a research study, normalized data, this is what they've done to it. Your norm reference tests that you took in high school, the Wisconsin state tests, they normalize the data. What a z-score is for an individual value, it is that number minus the mean of that set of data divided by the standard deviation of that set of data. Now that number itself has meaning, but it also has more meaning when we use it to compare it to other numbers. Let me show you what I mean. To get into school, many of you had to take an entrance test. Let's say you had to take a math test and an English test. Boo, English, right? Sorry. Let's say on the math test, you score a 68. On the English test, you score an 81. Which test did you do better on? Well, it's really easy to say the English, right? But that could have been an easier test. So to compare, what you really need to do is compare back to all the other people that have taken each of those tests. So let's say of all people who took the math test, the mean score was 62 with a standard deviation of 4. That's for the English test. For all people that took the English test, the mean score was, let's see here, 71 with a standard deviation of 7. Now you might look at this and say, well, I only scored 6 points above the mean on the math test. I was 10 points above the mean on the English test. Still looks good for the English test, doesn't it? But let's look at that z-score. The z-score for the math test. What was your score? 68. So we start with the 68. We subtract the mean, which was 62. Then we divide by standard deviation of 4. So 68 minus 62 is 6. 6 divided by 4 is 1.5. Now, like I said, that z-score in itself has meaning. What that means is you scored 1.5 standard deviations above the mean on that test. If you're looking at the bell curve, here's the mean, there's 1 standard deviation, there's 2 standard deviations. Your score is right in here, between 1 and 2 standard deviations above the mean. Not bad, right? Let's do the z-score for the English test. What's your score? 81. We subtract the mean of 71, and we divide by standard deviation of 7. So 81 divided by 81 minus 71 is 10. 10 divided by 7 is approximately 1.428571, right? We'll say 1.43. So on the English test, you were only 1.43 standard deviations above the mean. So if I put that on this bell curve, you were slightly below the math. So it's a way of comparing two scores or two numbers that come from different populations by comparing them back to their own population and seeing which one stands higher. Now, an example, now this is more of a business example than a healthcare example, and I apologize for that, but my creativity is kind of sapped on a Friday morning. Let's say you are managing, you could adjust it for managing any type of facility, healthcare or whatever. Let's say you are managing a department store and you need to fire one salesperson. Some days doesn't that sound like a great stress relief? Why you're fired, your stuff and go home. We've narrowed it down to 2 salespeople, Bob and Steve. Will you decide that next week, whoever has the worst week of sales is out the door? So for that week, let's say Bob's sales are $2,700. Steve's sales are $4,200. Bob was 27, Steve is 42. But now let's be fair here. Bob works in toys. The mean sales for all people that worked in toys was $4,100 with a standard deviation of $600. Steve is lucky enough to work in electronics. For all people that work in electronics, the mean sales were $6,500 with a standard deviation of $1,000. You think Steve's out the door? Let's take a look. Let's do the Z-score for Bob. Where do we start? 2,700 minus 4,100 divided by 600. Good. The value minus the mean divided by the standard deviation. 2,700 minus 4,100 is negative 1,400. Divided by 600 is negative 2.333333. Negative 2 1/3. Bob is, the negative means that they're below the mean. So Bob's sales were 2 1/3 standard deviations below the mean for that department. Let's look at Stevie. What do I do for Stevie? Probably shouldn't call him Stevie if I'm about to fire him. 4,200 minus 6,500 divided by 1,000. What's 4,200 minus 6,500? Negative 2,300. Divided by 1,000, which is a negative 2.3. Bob was slightly worse. Negative 2.3 is a little bit further below the mean than negative 2.33 is a little further below the mean than just negative 2.3. So Bob just messed it. So goodbye, Bob, yes. Should have bought something for the kids at home, huh? So that Z-score is another very powerful. The last thing I want to talk about before we hang her up for statistics, I do want to do just a little bit of a plug. Many of you in the nursing program will go on to a 4-year university. One of the classes you will have to take is a full-blown statistics class. So any of you, if you find that you have time, a gap between taking your generals and getting admitted into clinicals through that petition process, that is one option, is to pick up a statistics course in that semester. WITC only offers the statistics course in the spring. It's only offered online, but you can find it through other institutions as well. Well, the problem is most of them that are good accredited institutions are more expensive than us. Like UW Eau Claire is about 2.5 times what we pay. And like Franklin University does it online and does a very good job of it. That's where we got our curriculum from, was Franklin University. Yes, they're out of Columbus, Ohio, but they're about 3.5 times as much accredited as we are. It is online, but ours is online in the spring, and theirs is online 3 times a year, spring, summer, and fall. What's that? Lakeland College offers that, but you have to go to Chippewa Falls to take it. UW Eau Claire, UW Stout would all offer it. The main advantage of WITCs is it's less than half the price of any of the other ones. Okay. Yeah, we don't offer a whole lot in the summers here anymore. So what we want to talk about, our last subject we want to talk about, is percentiles. Percentiles is kind of that measure of position. Pretty much all of you have heard the term percentile come out. Whether it's, you took a test and you're told you tested in the 84th percentile, or if you have kids and you're told your kid is in the 73rd percentile for height and maybe the 91st percentile for weight or whatever. What do those mean? Well, that means a percentile is the percent of other, percent of, let's try that again, of others who are smaller. I blacked out on how I was going to say that for a second. Now, by others, it may not be people, it means numbers. So if you're taking a test, that's the percent of other scores that were smaller than your score. If you want to find the percentile within a set, it's very much like our median calculation. First step is you have to put them in order. Second step is you have to find the position. Now, the best way to do this, to describe this, is to do some examples. So I'm going to give you, we're going to make a set of numbers here. I am going to put them in order as I make them just to save us that step. So normally you would have to put them in order first. One, two, three, four, 45, and 57. So there's our numbers. For this set of numbers, what would n equal? There we go, 12, perfect. There are 12 numbers in this set, so n would equal 12. So to find the position, it depends on what percentile we're looking for. Let's say we're asked to find the 60th percentile. Well, the location is going to be n times the percentile. So n is 12. What's the percentile? 60th, so that's 0.6. 12 times 0.6 is 7.2. When we did the median, when we got a decimal, what did we do with that number? We rounded up. Even though it's only 7.2, we still round up. The eighth, because it's the, you got to be the numbers that are smaller than it. So if we round it down, it wouldn't be smaller than that number anymore. Let's say the eighth number in the list is the 60th percentile. So 32 is the 60th percentile of that set of numbers. What if I asked you to find the 25th percentile? Well, that would be 12 times what? 0.25. Very good. And what's that give us? 3. Now remember in our median, when we got a whole number for that, it was between that number and the next. So that's telling us our 25th percentile is between the third and fourth number. Third number is 5, fourth number, or 25, the fourth number is 26. So the 25th percentile is found 25 plus 26 divided by 2, or 25.5. 25.5 is the 25th percentile. You only round up the position, not the number itself. In your notes, I'm going to have you take a minute and find the 75th percentile for me. So you do 12 times what? 0.75, which gives you 9, which is telling us it is between the 9th and 10th. So the 9th is 35 and the 10th is 39. 35 plus 39 is 74, divided by 2 is 37. So the 75th percentile is 37. The other process we can do is find what percentile a number is. To do that, we're looking for the decimal location again. To find what percentile the number is, we're going to find the number that are smaller than it plus 1/2 times the number that are equal to it divided by n, the total number of numbers. So for this set of numbers up here, let's say I want to find the percentile of 45. Bless you. So if I look up here, how many numbers are smaller than 45? Here's the 45. How many are smaller than that? 10 are smaller, and how many are equal? 1. Yep. So there's 10 that are smaller plus 1/2 times the one that's equal. N, of course, is still 12. So 10 plus 1/2 times 1 is 10.5. 10.5 divided by 12 is 0.875, I believe. So that is the 87th.5 percentile. I might ask what percentile is, I think it's 26 is the one that's repeated, yes. It's 26. So I'm gonna go back up here to my list. Here's the 26 right here. I'm gonna erase this. There's 26, it appears twice. How many are smaller than 26? 3, and how many are equal to 26? 2. So there are 3 that are smaller, plus 1/2 times the 2 that are equal, divided by 12. So 3 plus 1/2 times 2 is 4. 4 divided by 12 is 0.333. So that's 33.3 third percentile. So here's the question. Is the 50th percentile good or bad? If you're told that your child is at the 50th percentile for development, is that good or bad? Yeah, 50th percentile would be dead in the middle. They are exactly average. If you're looking at the bell curve, 50th percentile is right there. So they're saying your child is average. So a lot of people see 50th percentile and say, oh, that's horrible. No, that's in the middle. You're average. Not everybody's 90th percentile. Okay, so do you guys have any questions on statistics? There will be from statistics. You will have mean, median, and mode. You'll have standard deviation. I promise I won't put more than like 10 numbers on there for standard deviation calculation. I had a professor in college that gave us like 25 numbers to calculate the standard deviation by hand. I spent some time looking for his car. So anyway, I'm just kidding, by the way. You'll need to know z-scores. You'll need to know the empirical rule. Remember the empirical rule, that's the curve with the percents in it. So make sure you have that page 355 marked off in your book, or have the page in your notes with the percents and the curve marked off so you can find it. You'll need to know how to organize data. That could either be into a frequency table or some sort of basic graph. And you'll need to be able to read graphs and tables as well. Now that's the statistics side of it. Remember, there's still the graphing. So on graphing, you'll need to be able to fill in a table and plot points. You'll need to be able to graph a line using the slope and the y-intercept. You'll need to be able to find the slope of a line. You'll need to be able to plot points and identify coordinates. Coordinates that x, y, ordered pair. And here's the one that most people struggle with a bit, and that is the variance. That's the direct and inverse. So what we've done today, we finished up all the homework assignments that are plotted in Blackboard for this final unit. There are a ton of pages here, so I will just list the pages. 321, 326 to 330, 339 to 340, 347 to 348, 353 to 354, 357 to 358, 359, and 363. As I said, these pages are listed in that table in Blackboard under course information. All the pages and the assignments that are listed in that table are due then, like we said, say May 14th, that Wednesday. May 16th is Wednesday. You can turn them in when you take your test, yes. But the homework does have to be submitted by May 16th. Remember, if you want to do corrections on test 3, make sure you get those to me by next week. These are just all, yeah, it says in Blackboard what the problem numbers are. I just want to write them all out. It is, if you just do the odds on each of those, that will cover it. Anybody have any questions before we go? Yep. Then you're done, yes. Unless you want to do corrections on the test. Yes, corrections have to be submitted before, actually the 17th for corrections. After that Thursday. Okay, well, you all have a great week. I will see the network will stay open here for another half hour. If you want to start working on homework and ask any questions, I'll be here. Otherwise, we'll see you next week for the test.